So we've spent a good bit of time talking about finding roots or solutions of polynomial equations in the last few lessons. I'd like to close this discussion in this lesson by sharing with you two additional tools for locating the roots or knowing how many you should have. These two tools are known as Descartes' rule of signs and the fundamental theorem of algebra. Let's start with Descartes' rule of signs. So Descartes' rule of signs is named for René Descartes, a French mathematician and philosopher born in the late 16th century, 1596 to be exact. Descartes is known for lots of things, including his famous quote, "I think, therefore I am." The Cartesian plane, or the XY plane as we sometimes call it, bears his name. His rule of signs is what I want to focus on in this lesson as we finish this study of finding roots of polynomial equations. Basically, this rule can tell us quickly how many positive and how many negative roots we have for a polynomial equation. It does not tell us where those roots are. It just gives us an idea of how many positive and negative roots we might have. So even though it doesn't tell us where they are, the rule can still be very, very helpful. I think the best way to describe this rule is by walking through an example. So let's do that here, and then I'll try to talk about the rule in a little more theoretical way later on. Let's look at the following and determine how many positive roots and how many negative roots there are for this equation. 5x to the 7th minus 8x to the 6th plus 19x cubed plus 2x squared minus 14x minus 8 equals 0. Now, as I start this example, let me point out, and I need to make this very clear, that Descartes' rule of signs is going to tell us the possible number of positive roots and the possible number of negative roots that this equation can have. It doesn't care about whether the roots are rational, nice fractions like we talked about in the previous lesson, or more complicated real numbers like 4 minus the square root of 7, that's a real number which is not rational. So Descartes' rule of signs is not only worrying about rational roots, it's worrying about all real roots. Now, let's see how it works. The rule first says to start with the polynomial in standard form, and that's the way our left-hand side already looks, and it asks us to see how many times the sign changes as we read the polynomial from left to right. So let me remind you again, the polynomial that we have is 5x to the 7th, that's positive 5x to the 7th, minus 8x to the 6th, plus 19x cubed, plus 2x squared, minus 14x, minus 8. Now the signs, when you look at them in pairs, go as follows. First you have a plus and then a minus. And then if you look at the next pair of signs, you would have a minus and then a plus. And then you would have a plus followed by a plus, and then a plus followed by a minus. And lastly, the last two numbers are both negative, so you'd have minus, minus. Now, did you notice there that you actually had three sign changes where we either went from a plus to a minus or a minus to a plus when we were looking at those pairs? Descartes' rule of signs tells us what that means. It means that the possible number of positive roots for this equation is either 3, which was the number of sign changes that we saw above, or 1. Now, where did this 1 come from? Well, once you see the exact number of sign changes, then you start from there and you keep subtracting down by 2 to see all the other possible amounts. So, for example, if the number of sign changes had been something like 7, let's say, then the number of possible positive roots would have been 7, or 5, or 3, or 1. Okay, now that's the positive possible roots. What about the negative ones? What about the possibilities for the number of negative roots? Well, Descartes tells us how to do that as well. Go back to the original polynomial, and everywhere you see an x, plug in negative x in the whole polynomial. In this case, that would give you the following. 5 times negative x to the 7th minus 8 times negative x to the 6th plus 19 times negative x cubed plus 2 times negative x squared minus 14 times negative x minus 8. And now you simplify this. And when you do, you'll have negative 5x to the 7th minus 8x to the 6th minus 19x cubed plus 2x squared plus 14x minus 8. Now, again, look at the pairs of the sign changes. First, you're going to see a negative 5 with a negative 8, so that's going to be a minus minus. Then the next pair is going to be minus minus again because you have a negative 8 with a negative 19. Then you have a negative 19 with a positive 2, so that's a minus plus. And then you have a plus plus, and the last pair of signs is going to be plus minus from the plus 14 and the negative 8. Now, how many changes of sign do you see in those pairs? Well, there's exactly 2. One of them went from a minus to a plus, and one of them went from a plus to a minus. And Descartes' rule now tells us the following, that the possible number of negative roots is either 2, which was the number of sign changes we saw, or 0. Remember, we start with the number of sign changes that we see, and then we keep subtracting down by 2 until we either hit 0 or 1. Those are the only 2 possibilities. Okay, so in this problem, we now know that the possible number of positive roots is either 3 or 1, while the possible number of negative real roots is either 2 or 0. Well, how might that help me? Well, for example, let's say we found out that a certain negative number was a root. Well, since the possible number of negative roots is either 2 or 0, if we found one number which was a negative root, we would know that we'd have to find another one which is also negative so that we could get up to the 2, because the only 2 possibilities were either 2 or 0 for the number of negative real roots. So Descartes' rule of signs is great for checking our work and also for making sure we've done everything that we need to do. Now, it turns out that the original equation I gave you, 5x to the 7th minus 8x to the 6th plus 19x cubed plus 2x squared minus 14x minus 8 equals 0, actually has exactly 1 positive real root, you can actually find it, and 0 negative real roots. And those fall into what Descartes' rule of signs told us as the possibilities. Now, by the way, did you notice that there were some terms missing in the original polynomial? I actually did that on purpose. Like there was no x to the 5th term. What do? Why didn't I try to do anything with that? Well, it turns out it's not a problem if a term is missing. You just skip right over those and do just as we did. So if you have a term that's missing, like an x to the 5th was missing earlier, you simply ignore it. Don't even look for it and just keep doing the problem as we just did. Now, let's look at another example. I'm going to suggest you try this one first on your own, and then we'll check back together to see how you did. Determine the number of possible positive roots and the number of possible negative roots for the equation 2x to the 4th plus 5x cubed minus 2x minus 5 equals 0. Okay, let's look at the number of sign changes in the original polynomial thanks to Descartes' rule of signs. Remember, you've got to have that polynomial in standard form. Thankfully, I wrote this one in standard form for us. If it hadn't been, you'd have to rearrange the terms until the highest power term was in front, and then the rest of them descended from there. So the original polynomial is 2x to the 4th, that's plus or positive 2x to the 4th, plus 5x cubed minus 2x minus 5. Well, the signs there go plus plus, that's for the plus 2 and the plus 5, and then a plus minus for the plus 5 and the minus 2, and then a minus minus from the negative 2 and the negative 5. So there's exactly 1 sign change in these pairings. Descartes' rule now tells me that there must be exactly 1 positive real root for this equation. That was the number of sign changes we just saw, 1. And of course, you can't subtract 2 there, because if you took 1 minus 2, you get negative 1, and it makes no sense to have negative 1 real positive roots. So we're going to have exactly 1 positive real root for this equation. That's cool. It tells me I need to go find that in just a minute. Now, what about the possible number of negative real roots? Well, remember what the rule says to do. Go back to the polynomial, replace all the x's by negative x. And when you do that, you're going to have 2 times negative x to the fourth plus 5 times negative x cubed minus 2 times negative x minus 5. Simplifying a bit, you'll end up with positive 2x to the fourth minus 5x cubed plus 2x minus 5. Now let's look at the sign changes of this new polynomial. Now they're going to go plus minus, followed by a minus plus, followed by a plus minus. There are actually 3 such changes there, and that means the number of negative real roots must either be 3 or 1 when you subtract 2 out of 3. So now you know quite a bit from this example thanks to Descartes' rule of signs. And you know that you have to have exactly 1 positive real root and either 1 or 3 negative real roots. Now, you might recall that we actually studied this particular problem in a previous lesson. If you don't remember, it's okay. I won't blame you. But let me remind you of what we found in a previous lesson. Using the rational roots theorem, we were able to show that x equals 1 and x equals negative 5 halves are roots of this equation. So we already know of 1 positive root, that's the x equals 1, and 1 negative root, x equals negative 5 halves. Both of those are real numbers, 1 and negative 5 halves. So what can we conclude thanks to Descartes' rule? Well, we know that the x equals 1 is the only positive number which is a root, because remember, Descartes had already told us there was only 1 positive root that was going to be available. And we know that there might either be 0 additional negative roots, because x equals negative 5 halves is a negative, or there might be 2 others. Remember, Descartes said that there would either be 1 or 3 negative roots in this case. In fact, if you just look at a graph of the polynomial, we can actually see that there aren't any more roots other than the 2 that we've already mentioned. Remember, roots of that equation correspond to x-intercepts of the graph of the polynomial. So, thanks to that work, we know that we're done. There's exactly 1 positive real root and 1 negative real root. Okay, let's look at one last example to see how useful Descartes' rule of signs can be. See if you can find the answer before I work it out for you. Let's find the possible number of positive real roots and the possible number of negative real roots for the equation negative 4x cubed minus 32 equals 0. Okay, let's start with the positive roots. There's only 2 signs here in the polynomial. It's kind of a short polynomial, and they're both minuses. And that means that there are no sign changes in the original polynomial on the left-hand side of the equation. Thanks to Descartes' rule of signs, it means that there are no positive real roots for this equation. So if I walked up to you and said, hey, I think x equals 4, or x equals 10, or x equals 23, I think those are roots, you could immediately tell me that I was wrong because 4, 10, and 23 are positive, and Descartes' rule of signs rules those out, pardon the pun. So let's look for negative real roots then. What happens if I replace the x by negative x? Remember, that's what you have to do to check for negative roots using Descartes' rule of signs. Well, when you plug negative x in, you're going to have negative 4 times negative x cubed minus 32. And that first term is going to actually become positive 4x cubed, and then you'll have minus 32 after it. Now look at the signs. You have a plus for the plus 4, and then a minus for the negative 32. And that means you have exactly 1 sign change here. And what does Descartes' rule of signs tell me then? It tells me that there must be exactly 1 negative real root. And it has to be there. There has to actually be 1 there. Now, can we find it? Well, let's go back to the original equation, and let's see if we can find that 1 negative real root. We had negative 4x cubed minus 32 equals 0. If we just multiply through on both sides by a negative 1, that's the same as 4x cubed plus 32 equals 0. Of course, a negative times 0 is still 0. Factoring out the 4 that's common, you'll have 4 times the quantity x cubed plus 8 equals 0. And you can divide that 4 out, and 0 over 4 on the right-hand side will still be 0, and you'll be left with x cubed plus 8 equals 0. Now, just subtract that 8 over to the right-hand side, and you'll have x cubed equals negative 8. Now, here's a question. Do you know a negative number which satisfies x cubed equals negative 8? Sure. Take negative 2 for x. Negative 2 cubed is negative 8. And so thanks to Descartes' rule of signs, I knew there was a negative real root out there. Now I know from the work I just did, it's x equals negative 2, and I don't have to look for any others because Descartes' rule of signs told me there were no positive real roots and there was exactly one negative real root. Now, let's transition to our other very important root finding tool for this lesson. It comes from something called the fundamental theorem of algebra. Now, before I get to this tool, I have to make a confession. Just like with Descartes' rule of signs, this new rule isn't going to tell me where the roots are. Did you notice how Descartes' rule of signs was useless for telling me exactly what the roots were? It was just telling me how many there might be. Unfortunately, this new tool is going to be the same way. Even so, it's an amazingly important rule. So let me talk you through a little bit of mathematics just to show you what this new rule is. First, let me state the fundamental theorem of algebra. Now, this way of stating this doesn't look like it's going to help much, but let's state it this way first. If you have a polynomial p of x and it has degree at least 1, then the equation p of x equals 0 has at least one root. Now, that root might be a rational number like 2/5, or it might be a real number that's not rational like 4 minus the square root of 2. It might actually even be a complex number with that I equaling the square root of negative 1 sneaking in somewhere. But the point is that the equation must have at least one root. So that's what the fundamental theorem of algebra is trying to say. Now, it might not look like that's going to help, but let me show you a byproduct of the fundamental theorem of algebra, which is extremely helpful. And this is the tool that we want to include in this lesson. If you count all the roots of an equation, rational, real but not rational, like 5 plus the square root of 10, or imaginary as well, where you have to include the I equaling the square root of negative 1, and you count all the roots in terms of how many times they appear, even if they appear multiple times, then it turns out that an nth degree polynomial equation has exactly n roots. So for example, if you have a polynomial of equation of degree, let's say 5, and you set that polynomial of degree 5 equal to 0, the rule I just told you tells me that there must be exactly 5 roots as long as I count how many times each root appears. One root might actually appear 2 or 3 times. And as long as I count the rational ones, the real ones which are not rational, as well as the imaginary ones. That's what the rule says. So let me try to demonstrate that with a few examples. Consider the quadratic polynomial equation x squared minus 14x plus 15 equals 0. I know from the quadratic formula that I can find the roots of this thing really quickly. And they're going to be x equals the negative of negative 14 plus or minus the square root of negative 14 squared minus 4 times 1 times 15 divided by 2 times 1. And if you do the arithmetic, and we've done it several times in other lessons, you're going to find that the roots are x equals 7 plus or minus the square root of 34. So I have 2 roots. One of them is 7 plus the square root of 34, and the other is 7 minus the square root of 34. Now, thanks to this rule that we quoted, which was a bit of a byproduct or a spin-off from the fundamental theorem of algebra, I know that that's the only 2 roots. And notice that they're both real numbers because they don't require us to consider any square roots of any negative numbers. So we had a second degree polynomial, and I found 2 roots with the quadratic formula. Those 2 roots are the only 2 because the polynomial in question had degree 2. Okay, let's try another example. Let's take the polynomial equation 4x squared minus 20x plus 25 equals 0. We know that this must have exactly 2 roots because it has degree 2 and thanks to the fundamental theorem of algebra. Now, it might not be two different roots though, so let's be careful. What are those roots? If you stare at that polynomial long enough, you realize that the left-hand side actually factors. And it factors as 2x minus 5 times 2x minus 5, and then you set that equal to 0 for the right-hand side. Now, there's a root then that's trying to sort of jump out at you off the page, namely x equals 5 halves. Just set 2x minus 5 equal to 0, add 5 to both sides, and divide by 2, and you'll see the root 5 halves appears. And now I can hear some of you saying, wait a minute, I thought there were supposed to be two roots. Where's the other root? Well, the other root is actually 5 halves again, if you will. I didn't say that the fundamental theorem of algebra told me they had to be different roots. Remember that it says once you count the roots and you count the number of times that each root appears, then that will have to equal the degree of the equation. Notice that 5 halves is a root from the equation, but it's going to be a root from the first factor of 2x minus 5, and it's going to be a root from the second factor of 2x minus 5. So actually, you would have to count the 5 halves twice. And since the degree of the polynomial was also 2, you know you're done. There are no other roots. Okay, let's try another example. And again, we're just trying to practice with this fundamental theorem of algebra and its byproduct. Let's look at the roots of, or find the roots of, x cubed minus 4x plus 15 equals 0. Now, let's try to put together all the things we've learned up to this point, or at least some of them, and see if we can actually find all of these roots. First, the fundamental theorem of algebra tells me how many roots there have to be as long as I count how many times each root will appear. Remember, the fundamental theorem of algebra, or at least the byproduct of it, is that an nth degree polynomial equation will have exactly n roots. Some of them might be complex or imaginary. Some of them might be real. Now, how many roots then are there for the equation x cubed minus 4x plus 15 equals 0? Well, the answer is easy. It's 3, because I have a cubic polynomial on the left-hand side. And again, remember that 3 might be counting how many times the same root appears. It might appear twice, for example. But where are those roots? Okay, I know how many I need to find. Let's find them. Well, according to Descartes' rule of signs, I should be able to at least try to locate how many positive and how many negative roots there are. Well, we did several examples with Descartes' rule of signs, so I think we can go through this pretty quickly. Let's go back and look at the equation once again and try to see how many possible positive roots there are. Remember, you're looking at x cubed minus 4x plus 15 equals 0. When you look at the sign changes of that, you're going to have plus minus, and then you're going to have a minus plus. And so you have two sign changes. So Descartes' rule of signs tells me that the number of possible positive roots for this is going to be either 2 or 0. Okay, that's the positive roots, or the possible positive roots. How about the negative, potential negative roots? Well, let's go back and look at our equation again. You're going to have x cubed minus 4x plus 15 equals 0. And now remember what you have to do to find the negative roots in Descartes' rule of signs? You have to replace x by negative x. So we're going to have negative x cubed minus 4 times negative x plus 15 equals 0. And that's going to equal negative x cubed plus 4x plus 15 equals 0. And the sign changes will be negative positive and then positive positive. So how many sign changes did we have? Actually, just one right at the beginning, negative positive. So how many possible negative roots will there be from Descartes' rule of signs? Exactly 1. So let's figure out what we've learned so far. We know there have to be 3 roots thanks to the fundamental theorem of algebra. And now, thanks to Descartes' rule of signs, I either have 2 or 0 of them being positive, and I have exactly 1 negative real root. And keep in mind, Descartes' rule of signs is only trying to keep track of the real roots. It has nothing to do with the imaginary or complex roots that might show up where you have to have a square root of -1 thrown in or the value I. Okay, so far so good. Now we've used a few tools already. Let's go work with the rational roots theorem to see how many of these possible real roots from Descartes' rule are actually rational roots. Okay, so now I need to look at the equation again, and remember the rational roots theorem says that any rational roots are going to be a divisor of the constant term divided by a divisor of the leading coefficient. So in this case, my constant term is 15, and my leading coefficient is 1. And so the possible rational roots of this equation are going to be something like 1 over 1 or -1 over 1, and then possibly 3 over 1 or -3 over 1, 5 over 1 or -5 over 1, and 15 over 1 and -15 over 1. And since all of those are divided by 1, I can just write them as whole numbers as 1, -1, 3, -3, 5, -5, 15, and -15. Now those are the possible rational roots in this case. Now I suggest we look at the negative numbers in this list to see if one of them is the negative real root that was already predicted by Descartes' rule of signs. Notice how we're sort of bringing all these tools together. So I'm going to suggest that you check to see if x equals -1, -3, -5, or -15 is a root of the equation x cubed minus 4x plus 15 equals 0. Okay, did you find it? Well, let's see. We could try a few together here real fast. Let's plug in -1. When you plug in -1 and do all the simplification of the left-hand side, you're going to end up with the equation 18 equals 0. That's false. So -1 is definitely not the negative real root we're looking for. Let's plug in -3. When you plug in -3 and you do the arithmetic, you're going to end up with -27 plus 12 plus 15, and the right-hand side is just 0. But wait a minute, that's the equation 0 equals 0. And that's true. Now guess what we can say? We just found that -3 is a negative real root of this equation. But Descartes' rule of signs told me that there was exactly one negative real root. I just found it. So I don't have to check -5, and I don't have to check -15, which were on the list of potential real roots from the rational roots theorem. It would be a waste of time. Descartes' rule of signs says there was only one negative real root. I just found it. It was -3. I'm just going to throw -5 and -15 away because they're definitely not going to work. So you see how that's a time saver? Descartes' rule of signs actually came to our help, and now we can do less work and we can move forward to look for other things. Now, let's remember another tool that we saw recently. If x minus 3 is a root of the equation, then the factor theorem tells me that x minus -3 or x plus 3 must be a factor of the left-hand side. So I'm going to suggest that we factor that out with long division and see what the left-hand side looks like once we do the factoring. So let me suggest that you now divide the original left-hand side, which was x cubed plus 0x squared minus 4x plus 15. Remember to add that 0x squared in there if you're going to do long division. Divide that quantity by x plus 3 and see what you get. Well, first of all, you should have gotten a division that had 0 remainder because x plus 3 is supposed to be a factor of the original polynomial. And secondly, what you should have gotten was x squared minus 3x plus 5 as the final answer of that long division. And that means that I can rewrite my equation as x plus 3 times x squared minus 3x plus 5 equals 0. Now you might say to me, well, how do you get that? Well, the long division actually does it for us. Now, let's see. Can we find the rest of the roots? That's what we were doing in the first place. Well, you know what root comes from the x plus 3. That was the -3 that you already found. So now let's look at the other part of the polynomial, x squared minus 3x plus 5. Can we find the two roots that are there? Well, of course. Use the quadratic formula. How many tools have we used in this example? Tons of them. But these are all great tools. And when you use the quadratic formula, and you just go through the work, you're going to see that the equation is going to have the roots x equals 3 plus or minus square root of negative 11 divided by 2. So there are your other two roots, 3 plus the square root of negative 11 over 2, and 3 minus the square root of negative 11 over 2. But I want you to notice something. Those are complex numbers. They're not real numbers because you're taking the square root of a negative number. That's okay though. We knew that there had to be 3 roots. We now know what they are. One of them was the real number, x equals negative 3, and the other two are 3 plus square root 11 times I divided by 2, and 3 minus square root of 11 times I divided by 2. And that means we're done. It also means, by the way, if we were to graph the polynomial we started with, x cubed minus 4x plus 15, we would only see one x-intercept because that would correspond to the negative 3 root. The two complex roots are not going to show up in any way on the graph because they're not real. So you would actually only see one x-intercept. Well, we've used a lot of tools today, and we've done a lot of examples of how to find roots thanks to all of these tools. I hope you've enjoyed trying to put all those together because they really are helpful once you learn how to master them all and once you learn how to use them in the right times. In the next lesson, we're going to shift our focus quite a bit, and we're going to study things like square roots, cube roots, and functions along those lines.